How to find the determinant and the inverse matrix. The inverse matrix for a square matrix, remember only square matrices have inverses, so the inverse for the square matrix ABCD has been shown in the notes to be a scalar, which is a fraction 1 over AD minus BC outside of another matrix like so. And you're probably wondering to yourself, how the hell do I remember this? And it just looks like a bunch of letters. And hopefully I'll be able to show you how you can easily remember the inverse matrix. Now I'd just like to cast your mind back to the identity matrix. Remember from the notes that the identity matrix is a special matrix where we have the value of 1 on the diagonals, and you'll notice that the diagonal for the identity matrix is that diagonal from top left to bottom right, and that's the diagonal for the identity matrix. And the diagonals play a part in inverse matrices. So if we look at the diagonals there, across there we have DA and we have BC, and these diagonals are going to play a part. So let's just put the identity matrix away for a little bit and have a look at our original matrix, which is A, B, C, D. And if I have a look at the diagonals of this particular matrix, across this diagonal I get A, D, and across this diagonal I get the values B, C, or CB, depending upon which way I look at it. And if I was to put a subtraction sign in the middle, you'll notice that this expression here is the expression here which we call the determinant. So by looking at the diagonals, firstly the same diagonal as the identity matrix, and then the other diagonal, we've got the expression for the determinant. Now looking at the inverse matrix here, we'll notice that the inverse matrix is related to the original matrix, but that the values in the inverse matrix are rearranged and revalued, and the diagonals once again will play a part in determining how this goes. So this diagonal here, A and D, which creates the first part of our determinant, we should notice that the values in the inverse, the A and the D, they're swapped over, so they're reordered and they're swapped. So the A from here is swapped down to here, and the D from here is swapped up to here. And then the second part, the minus BC in the determinant, is from the other diagonal, the cross diagonal there, and that diagonal there, and we'll notice that they're both negatives. And if we just remember back to the diagonals help us for the determinant. The diagonals also help us figure out which values to swap and which values to make negative. So let's see if we can't use all of this to determine the inverse of this matrix here. So the first thing we need to do is to determine whether or not it actually does have an inverse. The determinant of our matrix here, remember that's AD minus BC, and in this case it's AD is 3 times 9, and it's minus BC, and so it's minus 7 times 5, and that's 3 nines are 27 minus 35, which is equal to minus 8. Now, if the determinant was 0, then there would be no inverse, but minus 8 is not 0, so there is an inverse. So the inverse for this matrix is -1 on 8 outside of, now we need to swap these two values around, 9, 3, and make the other diagonal negative, -5, -7, and that is our inverse matrix. So let's now look to determine the inverse of this matrix. The first thing we need to do is to determine the value of the determinant, and remember that will be 6 times 2 minus 2 times -1, and that will be 12 plus 2 is equal to 14, and that's not equal to 0. So this particular matrix does have an inverse. So the inverse of this matrix will be 1 over 14 outside of the matrix 2, 6, -2, and +1. And that's the inverse matrix. Two final examples. We want the inverse matrix of each of these. Well, this one is quite easy. It doesn't exist. Remember, only square matrices have an inverse. So if it's not a 2 by 2 or a 3 by 3 or a 4 by 4, then there is no inverse matrix. On this one up here, let's have a look at the determinant. It's 3 times 4 minus 2 times 6, which is 12 minus 12, and that equals to 0. So this one has no inverse either, because the determinant, or the inverse, requires to be 1 over the determinant, and this doesn't exist.